Good evening, everyone. Am I audible? Can someone please confirm if I'm audible? Yeah, thanks. Maybe we can start. Yeah, so welcome everyone to the live session for week 9 for the course Digital Circuits, which is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. I'm Anant Singhal, a PhD student at IIT Jodhpur, and today I'll be assisting in solving some of the assignment problems or some of the similar problems that have been given to you in your week 9 assignments. So, as you are already aware that we have almost covered the entire part of the course consisting of the combinational and sequential circuits. So today we'll be looking, so in the last week itself, we have covered this particular aspect, that is the data converters. We've already gone through the ADCs and DACs in the last lecture only. So in this lecture, we'll be more or less focused on the semiconductor memories. So the different kind of memories that we have in our syllabus contains ROM, SRAM, DRAM, etc. So in this, there are some explicit topics also that are not mentioned specifically, such as Hamming code correction and detection, and PAL and PLA are also different kind of circuits that are present. So yeah, we'll be more or less looking towards week 10 content in today's lecture, because week 9 content has already been covered in the previous lecture. So yeah, so with that, I think we can start the session. So the first problem that we have is each cell of the static RAM. Okay, so this will be static RAM. SRAM is already there. So this is basically a type of a memory, SRAM. So each cell of a SRAM contains. So if you already know the answers, you can type in the chat box, and then I'll also be explaining these things. Maybe a basic overview of these uh, different types of memories. So anybody who is already aware of this. Can someone confirm if it has already been taught in the theoretical lecture by Professor Shantanu? Okay, I've got one answer is A. Okay, so the answer to this problem is yes, it is correct that the SRAM contains 6 MOS transistors. So let me give you a very basic overview. So this SRAM you might have seen. So this is the fastest memory, and in your phones and laptops you might have seen a memory called as, or a memory assigned as, cache memory. So this cache memory is made out of this SRAM, and it is the fastest, and it is also called as 60 SRAM, where this denotes the transistors. So it contains 6 transistors, and as the name suggests, RAM. So RAM is a volatile memory. That is, it is not permanent. It is volatile in nature. So these are some of the things about this 60 SRAM. Similarly, so if I like broadly classify RAM as you have seen in the syllabus, so it can be either static or it can be either dynamic. So in this problem, we are particularly concerned about the static RAM. So let me try to give you a very basic overview of how a SRAM works, or what is this 60 SRAM. So this is a basic schematic of a 60 SRAM, in which you can see you have 6 transistors, which are namely M1, M2 until M6, and there are few different types of connections. So this is WL, which is also called as word line. This is the BL, which is also called as bit line. So I'm giving a very basic overview. I'll not go into very deep, but I'll try to explain how this particular thing works. So you can see that a circuit which is consisting of M1 and M2, if I make it, let's say, separately, so it looks something like this. So in this, it is M2, M1. We have a ground. Let's say we have a VDD here. Let's say this is input, this is output. You already might have seen in some of your basic circuit courses that this is nothing but a CMOS inverter, right? So M1, M2 is a CMOS inverter. Similarly, M3, M4 is also a CMOS inverter, and M5, M6 that you see are connected to both of these inverters. So if I talk in terms of like, okay, can I duplicate it? I cannot. Okay. So if I talk in like very simple terms, I can say M1 sorry, small M1, M2, and M3, M4. So these are the CMOS inverters, and M5, M6 in this particular circuit are called as access transistors. So this basically help you in accessing read or write operation of a SRAM. So this is a 60 SRAM. So as you can now see that so this is the input of the transistor. Let's say the X that I have denoted. This is the input of a transistor. Sorry, of the inverter M1 M2. So this the input of the inverter M1 M2 is connected to the output of the inverter M3 M4. Similarly, the input of the M3 M4, which is this cross, is now connected to the output of the M1 M2 inverter. So that is why these two inverters, that is M1 M2 M3 M4, we also call them as cross coupled inverters. This you all already might be knowing from your theoretical lectures also. So if I try to make a inverter, like inverter is nothing but a NOT gate. Let's say this is the inverter which is made out of M1 M2. So the output of this is connected to the input of the inverter, which is, let's say, made up of M3 M4, and the output of this is connected to the input of this. And then we have, let's say, access transistor, which are M5 and M6, for example. So this is what we call as, we have already seen in the first lecture of sequential lecture, that these are also called as latches. And this is nothing but a cross coupled inverter. Whatever you like give here, it holds it, and this is like holding memory circuit or the inside memory circuit. So this is what we call as latches also. So if I try to explain some of the operation that happens in a SRAM, it's basically, so SRAM can do three types of operation. The first one is read, the second one is write, and the third one is hold. So okay, let me try to explain the very basic operation, which is, let's say, the hold operation, which is this one. So just to hold the data whatever is there in this, so as I said that this is the latches, so this is the storing part of the SRAM. So this is where the data is stored. So what we do for the holding operation, just to hold this, what we do is we make our word line is equals to 0. So once we make our word line equals to 0, so these M5 and M6 transistor both are NMOS. So if you apply a 0 voltage at the gate, these both will be disconnected. So the only circuit that we are left with is this particular block, right? So this block is nothing but a latch. So basically, if you, let's say, if you have a 0 here, the inversion of that will be 1, and 1 will get again 0. So this will be like a hold circuit. So to hold it, you just make the word line to 0. So this is the first operation. I mean, this is the easiest operation to understand in an SRAM. So similarly, if I try to explain, let's say, the read or the write, okay, let me try to explain the read state first, because that is again a easier operation. Yeah, I thought, can I do that? Okay, I cannot. Fine. So let me, maybe I'll make a circuit quickly.
Sir,
Yes.
sir, when M5 and M6 are turned off,
Yeah.
um, how did the inverters are connected, sir?
Oh,
Like,
so inverters are already connected. I mean, this circuit you see, this block is already connected. I mean, wait. So this connection is always there, right? I mean, if you see that M5 and M6 are connected externally to one of the input of those transistors, right? So you are breaking it from here, basically. You are open circuiting M5 and M6. Hence, you are only left with this latch circuit.
yes. I mean, sir, here, where is that connection, sir, between M1, M2 inverter and M4, M3 inverters? Where
Oh,
is the connection?
so this connection is there, right? The crosses that I made, maybe if you see this. So this, yeah. So if you see, this is M1, M2, input of M1 and M2, this green dot. this is connected to the output of M3 M4. Similarly, what I just said that the okay, I've said the input of the M1 M2, which is this connection, is connected to the output of M3 M4. Do you understand this?
Yes, sir.
Similarly, if you see here now, this thing which is M3 M4 input is connected to the output of M1 M2. So M3 M4 input is connected to the M1 M2 output. So hence there is this connection.
So, sir,
Yeah.
as long as VDD is present, it will hold like that only, like flip flop only, no, sir.
Yeah, it is a latch, yeah. So yeah, this will hold the data as you have not VDD but 0 at the word line. Because once you give, let's say, a VDD, these both transistor will turn on then, right? When you give a higher voltage to a gate, so this M5 and M6 will get turned on. I'm saying VDD, sorry, the word line is 0 currently. There is no VDD given.
I asked, sir, not that, sir. I asked M2 M4 above VDD is there, no, sir.
So those are for the working of the, so the basic inverter is like this. So we have a VDD at the uh, PMOS source terminal or the drain terminal, you can say. So this is actually an inverter. I mean, the VDDs should always be there. So, oh, so whatever the input is there, so whatever I give it here, let's say whatever the previous state of this circuit was there, it will hold that. Does it make sense? So that VDD is actually inside this. That is not here or here. Input or output does not depend upon, I mean, that is not equivalent to VDD. It will depend upon what was the previous state or what we are trying to hold using the particular circuit. The everything will depend. Let's say if it was 0 here, then this circuit will hold 0, and if it was 1 here, for example, so this circuit will hold 1. This VDD is only for the working or the proper functioning of the CMOS inverter. Make sense?
Yes, sir.
Okay. So similarly, if I try to explain the read operation now, which is the second operation. So in the read operation, what we do is we make the word line to VDD and we pre-charge. You already might have seen this on your theoretical lectures also, but yeah, I'll just explain this. You pre-charge both bit line and bit line complement to VDD. So now if we see the circuit basically, so maybe I can use some different color. So I'll use red color for read. So for red, what I have given, we have given this word line to VDD. We have pre-charged this bit line complement, which is this blue line, and this bit line to VDD. So now you see this VDD, which is this connection, sorry, which is this connection is connected to the gate of this NMOS. So what will happen if both are high? So this transistor will act like a short circuit, right? So we have a higher, or we say we have a high or a VDD here, right? So once we have VDD here, that is at the output or the input of this, what I can say, input of this M3 M4 inverter. So this cube, what is the input? Yeah, so the input of this particular inverter is Q complement, right? So for example, we have just made Q complement to VDD. So similarly, because of the inverter nature, the Q will become 0, right? Does it make sense, everyone? So basically,
Sir,
this Q, yes, yes,
this Q bar has make it Q to zero now, sir.
yes,
Sir, above, okay.
yeah, yeah, yeah. Yes, I'm listening. You just let me know
Uh,
what are you saying.
sir, this M6 also VDD, no, sir. So here zero, here VDD means M6 is like, how can it happen, sir? I mean, when Q bar is
Yeah.
zero, I
Hmm.
mean Q bar is one,
Hmm.
the Q will be zero now, sir.
Yes, yes, it will be 0, correct.
But M6 is turned on and VDD from the bit line will be come now, sir. Zero
Yeah, yeah.
VDD.
So okay, so you tried. So what we have done is we have pre-charged to VDD, but let's say this is VDD and this is 0. So this will be like reading of that particular bit. It is not writing anything. You see, I'm not flipping this bit. What I'm trying to say is, let's say once this is 0, so this is like 0 is nothing but acting like a ground, right? So it is just reading that particular bit. So what we have done is we started with a pre-charged VDD in both bitline and bitline complement, but this will not remain VDD because since this is ground, this will discharge, right? If we want to, let's say, write operation, we need to do, or we need to flip this bit to 1, then only whatever you're saying is applicable. Is it clear?
Yes, is it like shorting that VDD to zero, sir?
Yeah, no, no. Okay, so let me try to explain. So let's say I make M6 like this. So you have given VDD here in the circuit. It is VDD in the word line, but you have grounded this. So it will act like a short circuit, and the Q will become since the Q will be 0, so this VDD will get discharged. Because ideally, what you need is you need the complement of this to be here, right? We have just pre-charged this to VDD. So if this is VDD, this should go to 0, right? I mean, if bitline complement is VDD, this should be opposite of that. I have just pre-charged it just to make just to confirm that these both the transistor will get turned on. But ultimately, this will go to 0 in the read operation. It is just reading whatever is there in this particular what to say, cross coupled inverters.
Okay.
Yeah. So
So,
similarly,
hello.
yes.
So what is the types of application we these are used?
Okay. So the memory is used in every circuit that we use. Even in our phones, we have, as I said in the first problem, that the cache memory is made using SRAM. So in your phones also you have a lot of memory elements. You have SRAM, DRAM, etc. Then in your computer laptops you have memory. You might have, every time you buy a computer you must have seen that this GB RAM, this that GB RAM or ROM. So that is basically the actual applications of these memory circuits.
Okay, sir.
Yeah. So the next operation is the write operation. In this, what we do, this is also called as flipping the states. So the only difference between the read and write operation is the word line will remain to VDD, but now what we do is we make the bit line complement to VDD. Like we do not give any specific pre-charge, or the bit line is basically 0. Since the bit line complement is VDD, so by default the bit line will be 0. So it is not pre-charged. So let me now explain you how will it work. So let's say in the circuit initially Q is 1, so the Q bar will be 0, right? So let me go to the circuit. So what I have just said, this is VDD, this is VDD, because the word line is VDD, this is VDD, and since this is VDD, so the bit line will be 0. So the blue markers will now indicate the write operation. So as I said, this is VDD, this is VDD, so Q bar will be VDD or 1, right? Which I have just said. So since Q bar is 1, Q will be 0, right? So now what you see here is bit line is also ground. This is also ground, and yeah, we have a VDD here. So once we have grounded the bit line, what you see is, okay, give me a minute. I need to see. Okay, okay. Flip it. Okay, okay. So the okay. So please bear with me. So what I have just done is I give the bit line to VDD, the bit line to, or the bit line complement to VDD. So this is what is basically doing. This is making, okay, this bar is 1. Yeah. This is making or writing 0 to Q, right? We have just made the value of Q to 0, and since this is 0, so this transistor won't work. So we have write 0 to Q, right? Similarly, if you want to, let's say, write 1, so what we'll do is we'll just do the opposite of this. We'll give the ground to this and VDD to this. Does it make sense to everyone? So for writing 1, let's say case 2, I'll still keep the word line as VDD, but I'll do the bit line to VDD and the bit line complement will be 0. So this will write Q to 1, or you can say write 1 to Q. So hence, basically this is why the flipping of states, why do we call it? Because Q is changing from 0 to 1 in both of these different functions. I
Sir,
hope,
is it like set reset? Can we think like that, sir?
yeah, you can think like that, but yeah, we are giving some specific condition to get that set reset thing. So we need to have these parameters to, let's say, you can say set the circuit, and we can need to have these parameters to reset the circuit, if you want to give analogy like that. Is it clear to everyone? So yeah, this is like a very basic working of SRAM. Maybe professor might have gone through it in very detail, so you can see those lecture too. So now the next problem will be something based upon the different types of memory. So as I said, so we have two types of RAM. One is static and one is dynamic RAM, which is known as DRAM also. So anyone with this answer?
Sir, sir, can you show above slide, sir, please? 1 second, sir.
Yeah, yeah,
Can you show that we have seen the right now, sir? Can you show the read option operations?
yeah, yeah.
So both one should we give to BL and BL dash, sir?
Yeah, so we pre-charge them to VDD so that both of the access transistors should work. We are just reading whatever there is there in this particular whole circuit.
Okay, sir. Thank you, sir.
Yeah. So now for the DRAM, as I said, so we again have two types of DRAM. One we call as 1T, 1C, that is one transistor, one capacitor, and there is this 3T DRAM. So for this particular problem, we have need to find the minimum number. So one transistor can also make a DRAM if we have a capacitor in place. So again, just to like explain very basic operation of this. So these are two types of RAM. So this is 3T DRAM and this is 1T, 1C DRAM. So the operation of this is pretty easier to understand. So this cannot hold anything, but this can do read and write operation. I think you already might. Okay. So let's say we want to store 1 or store 0. So let me try to give you example. So what we'll do is we'll give this bit line BL1, bit line 1 to 1, that is VDD. So you can see this is connected to this. So this will be VDD and the word line or the right line should always be VDD. So once we have this and this connected, so this capacitor will get charged, right? Because this will act like a short circuit. So this X will become VDD, or this particular transistor, or sorry, node will be having high value. And this will, what it will do, this will turn this transistor on, this will act like a short circuit, right? So this basically, this node will be at 0. So what I have done is I have given, so this is 0. So let's say this node will be low or 0. So once I have given X, for example, I am calling this X. So this will be low. Similarly, if I have done, let's say, a 0 to here, let's say this is 0. So this capacitor would have, I mean, if there would have been any charge, so this would have VDD was here. So on making it 0, I think 0 will be here. Okay, not like that. So what we need to do for a uh, read write operation is this BL line 1, sorry, BL1 or bit line 1 should be 1. But what if you need to do the write operation also, this RWL line, read write line, should also be VDD. So once you make this VDD, this will become high. Just to explain in very simple terms, for example, this 1T1C, if you make the bit line or the word line VDD and this will be VDD, this will be like a short circuit. This VDD will get charged, or this capacitor will get charged. So this is basically storing VDD, right? So this is storing 1. Once you make it 0 again, sorry. So since this capacitor is charged to VDD, this will get discharged back and this will be storing 0. Does it make sense? I mean, this is a very basic working of actual DRAM.
Sir.
Yes.
Yes, sir. For writing, this WL should be VDD now, sir.
Yeah. So WL should always, so right line should always be VDD. I mean, the transistor will only turn on when this gate terminal will be equals to VDD. And for reading writing 0 and 1, this should be the condition. I mean, for VDD it will be VDD or storing 1, and for 0 it will be getting discharged and storing 0.
How can we, sir? I understood the writing part, sir. How can we read, sir?
Yeah, so I mean, just to read, I mean, this memory is fine for writing because we do not have any read line, right? So even if you want to read what is there, for let's say, if this capacitor already contain, for example, VDD, that is 1, and if you want to read this, you just turn on this, I mean, just give the VDD. So what will happen if both are VDD? We can, I mean, it is like a short circuit, and this will actually connect or short the circuit. So this is saying that we are reading 1, or the actual value is 1. Similarly, if it is 0, so let's say if it would have been 0, so the capacitor would have connected to this part and the VDD will get discharged, and again you are saying that it was 0. Does it make sense?
If it was VDD and CS was VDD,
Yeah.
then no charge will go now, sir, through M1.
Yeah. So that is what I'm saying na, that it is at VDD. So we are reading that it is 1. We are not writing anything.
So if we send VDD means it again give it it is remaining VDD means it is stored one like that we think.
Yeah. So we are reading round. We are not writing anything. This VDD was already there. You need to understand that difference. We are not writing anything. Is it
And if
clear?
it was grounded to zero means okay that last time we have stored it zero like that we will think,
Yeah.
sir.
So if you give 0, so this path, there is a discharging path then. So now you can see that this actually has a 0 there. If it was initially 0, does it make sense?
Yes, sir. So then until writing it will stay zero, no, sir.
Sorry, until what?
Until again we write it will stay to zero, sir.
Yeah. So the memory does not contain anything if you do not store anything to this, right? So yeah, it will be nothing once you do not save anything. I mean, like in your phones, if you do not save the data, the memory occupied will be 0, right?
What is the purpose of this CBL, sir? Then
Yeah, this is just a bit line capacitor. I mean, just to have, let's say, this bit line, I mean, just to have the safety of the circuit, you can say. I mean, this is for higher purposes, but yeah, you can say that once this bit line will be VDD, so this can also provide a charge, or this can also provide a part to store some of the charge. For the operation, this is not important currently. Is it fine? Yeah. So yeah, I mean, as I said, like this is a very basic version of what is the working of SRAM and DRAM. But yeah, in detail, you should be seeing the lecture given by the professor. He might have like spent hours of this to explain how exactly the circuit works. So yeah, as we have just covered what is how a DRAM works. So this is now the operation, or this is a question based upon that operation of this. So it says in the following 3T DRAM configuration, you need to first write a single binary digit 1. So, okay, let me this. So basically, this is D in, this is write, this is read. So this is W, this is R, this is V, and this is Y. I hope it is visible now. So it is asking to write 1. So basically, you need to write 1. So to write 1, you need to give W to 1, right? I just explained this. So once you make 1 and 1 here, this capacitor will get charged to VDD, right? So this will be 1. Is it clear till here? Please let me know if it is clear.
Sir,
Yes.
what is the parasitic capacitor discharge? What is it?
Sorry, can you repeat? Your voice is breaking.
Sir, in the question, it says assume the parasitic capacitor is discharge is given,
Yeah,
no,
so
sir?
parasitic capacitor is capacitance that is in between inside the transistor. So we have, I don't want to go in very deep, but yeah, so if you see a MOS transistor, so we have, let's say this is the gate terminal and this is drain and source. So even between drain and source, we have capacitance CGD, then we have CGS. So all these capacitor combines are called as parasitic capacitance. So this can also contribute to our actual capacitance. So by saying assume the parasitic capacitor is discharged, that means these effect is nil or zero. So there are no stored charges directly inside the transistor. So this is a like a ideal transistor. Clear?
Yes.
Yeah. So once we have a V here, then the question is saying then read it from the terminal Y. So Y is here. So once we have a 1 here, this transistor will turn on, right? So this will be like a short circuit, no? So once we have a short circuit, so this is nothing but 0. Is it clear to everyone? So now just to read this, you will make it 1. So Y will be 0. So okay, question was, what was the question? It says for this operation, what will be the correct polarities of W or Y? Okay, so W or Y. So let's say if I give you option 0, 1, 0, 1, 1, 0, just 1, 0, 1, maybe something like that. Can be different options. So W, so for the first operation, you need to write this, you need to make the W to 1. So W is actually 1. The actual answer I'm writing maybe above. Now this will make V to 1 and this will discharge. So the actual output, just to read this, you need to make the read also 1 and the output will be actually 0. So this will be the correct bit. So 110 is the answer. Is it clear to everyone?
So, but how we can implement this type of queries?
What do you mean by implement? This already a circuit there, right? So you will make this circuit to implement this. I mean, what exactly are you asking? I don't understand.
So, I want to ask that this type of circuit, how we can implement that?
Where do you want to implement this? Like in a hardware, right?
Yes, I hardware.
Yeah, so you take this transistor and connect it to capacitor, then connect this capacitor to these two transistors. I mean, they are available in the market if you want, if you're saying like that. If someone said to tell once more, okay. So the question says that we need to write 1. So to write 1, I have given the write bit to 1. To write this 1 or VDD here. So once we have both of these transistors connected to VDD, we'll get our output to be 1, or this capacitor will be basically gets charged to VDD. And once we have a high input in this transistor, this NMOS will turn on and this will be acting like a short circuit and this node will ground because this is now directly connected to ground. Now to read this ground, we need to make the read bit 1 or 2. We need to give something to the gate to turn the transistor on, and once we turn the transistor on, this will act like a short circuit and your output is 0, which is now the read output. So the answer, the question was asking W or Y. So W was 1, R was 1, and y was 0. Is it clear? Whosoever asked?
Sir,
Yeah,
sir, we have written as one no, sir. But we are reading as y. We have given data as one no, sir.
yeah.
But
So
we are reading y equal to zero now, sir.
yes, yes. So whatever the x is there, so the 3T DRAM works like that. Whatever the x is there, the output will be x complement. I mean, this circuit is an inverter actually. You will see in your lectures also, this is an inverter.
Sir, sir, can you explain, please, sir? If you write zero, can you show how it will show output as one, sir?
No, no. Okay, fine. So let's say this x is 0. Okay, if I let's say make,
Give input as zero, sir.
yeah,
D
yeah, yeah.
in
Yeah, so if
and
D is 0, so this node will be 0, right? Because this transistor is not turned on, right? There is capacitor is always discharged at the initial state. We always assume like that. So if this node is 0, this will not turn on. This transistor will not turn on, right? This is like a open circuit. And to read this, you will make this VDD, and this is the only connection that you have. So hence this will be this Y will be 1, because Y is only connected to this. There will be no connection here. This is like a floating node. Does it make sense to you?
sir, the node is floating now, sir.
Yeah, so there is no discharge. It is not connected to ground.
Reading is one, sir, but
Yeah,
how can that one comes to output, sir?
because oh, so that is the only connection, right? I mean, you see, okay, let me try to explain in basic words. So yeah, so what I'm trying to say is your drain is not even connected. So your, sorry, not VDD, but let's say this is connected to 0 volt, and this is from where you are reading. So let's say this is Y. And once you make the transistor gate voltage, I mean greater than that of threshold or high voltage, the transistor acts like a short circuit. No, oh sorry, what I have just said. No, 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 this is not correct. So since this is 0, your drain is not connected. So the only voltage that you see, let's say if you apply a KCL, so this Y will be plus minus VDD, right? So the voltage will be around these two nodes, the gate and let's say the source. So it will only read the VDD. There is no connection, or what I can say is it is gone. Like uh, this thing is gone. So it will only read VDD.
Sir, do we take output from VDD and vice versa? Sir, I mean, we here is a high input impedance now, sir, for MOS.
Yeah.
Wha-
See, no,
Read
you are
is
not.
one now, sir.
Yeah, yeah, I understand that read is one, but you are not trying to
How
understand
can
that.
this one come to vice? I am not able to understand this, sir.
Okay, so let me try to explain in very basic words. So let's say we have a MOS capacitor, oh sorry, no MOS transistor. Let's say this is VDD, and let's say this is 0. So let's say this is having some higher voltage, which I am trying to explain to you. Let's say this is maybe, if this is 1 volt, for example, let's say this is 0.1 volts and this is 0. So which one is the drain and which one is the source? The one with the higher voltage is always drain, right? Are you able to
Yes.
understand this? So that is why. So you are not, don't get confused that we are reading VGS. We are still reading VDS only, because now the drain is interchange. Drain source is interchange basically. Once you make this 0, this becomes source. This becomes drain. Is it clear?
But sir, that source one is, I mean, when the V is one, and sorry, when X is equal to zero, Q5, there Q2 is there, no, sir, Q2.
What? Could you repeat your last line?
When, sir, here X equal to zero, no, sir.
Yeah.
So Q2 2 is off now, sir. I mean, it's turned off now, sir.
Q2. Which one is Q2?
This, sir. I
This one?
mean, yes, sir.
Okay, yeah, it's
It
turned
is
off, right?
turned off now, sir.
Yes.
So source from source, how can it be seen as ground, sir? I mean, since Q2 is turned off, the source will see as that as an open circuit now, sir.
Yes, it is floating. Yeah, I do agree with that. I'm not saying that this is ground or something like that. I'm saying that there is no connection. Okay, you are not. I think I'm also not able to explain you exactly what I'm trying to say. Maybe for this particular thing, you can probably mail me because already 40 minutes are gone in the first problem itself. I'll try to explain you over email, or we can have a chat later. Is it fine?
Yes, sir. Sorry, sir.
Yeah,
Sorry, sir.
no problem, no problem.
We will discuss.
Yeah.
Yes.
Okay, so we have our next problem. How many data inputs and and address input lines are required for a 128K cross 16 memory? So anyone, I mean, this is again a simple question. So let me just give you the numbers. So for a memory, what we have is the data inputs that we have. We have address input lines. So these are the two technical terms that we have. For example, this is 128K 16. So in technical terms, we write this as 2 raised power p cross n memory unit, where this address input line is nothing but p, the data input is nothing but n, and there is one more term which is m, which is number of locations, and m is nothing but 2 raised power p is equals to m basically. So we can also write this as m cross n. So now the question says how many data input and address input. So data input is basically n and address input is basically p. So we can find this directly. So I hope you already know that k is nothing but 2 raised power 10, which is 1024 bytes. So I can write 128 cross 2 raised power 10 bytes cross 16. So 128 is 2 raised power 1, 2, 4, 8, 16, 7. So this is actually 2 raised power 7, 2 raised power 10 cross 16, which is 2 raised power 17 cross 16. So if I compare it with 2 raised power p cross n, so n is 16 and your p is 17. So n is a data input is n, so this is 16 and this is 17. So the correct answer is option D. Is it clear, everyone? 16, 17 months. I don't understand. What is your query? No, no. So the question is asking data input and address lines. So data input is actually n, which is your numbers, which is afterwards. So that is 16. And your address input line is p, that is coming out to be 17. So 16, 17 is correct. I mean 17, 16 is incorrect. Is it clear? Yeah. So let's move ahead quickly. So it says to construct a 1 mega cross 4 memory, the number of 64 kilo cross 4 memory circuit required is how much? So anyone who wants to try it, or shall I do it by myself? This is again a very simple question, but yeah. So you want to try it or shall I do it by myself? Okay, maybe take 2-3 minutes and then I'll solve it. Write your answers in the chat box. Any answer? Okay. Okay, just to clear a previous query, I just found out that this circuit is actually only to read or to give you the access when you have a V of 1 and your read output should be 0. To have your read output to be 1, you need to have an additional read write line, which is actually here. So this circuit has not given that particular, what to say, access. So to do that, we need to again pre-charge the bit line too. So that particular question is actually only that circuit will only work if you have a high at this particular node. That is when V is 1. Then only you can read 0 at the output. Is it clear? Whosoever asked that particular question.
Yes.
Yep.
Please, sir. Sir, so this VDD is connected to that Y port, sir.
Yeah, yeah, yeah. Exactly. So this is actually pre-charged to VDD. Then you make that VDD, then only there will be this connection or the turning on. And then you can read the 0 if it is there. I mean, for the opposite operation. So we have those different connections. We do not have this line in that particular question.
Okay, sir. So when M3, I mean, when it's not zero or turned off, it will read VDD only, no, sir?
Uh, yeah, yeah, yeah. So it will read VDD once this is short circuited.
Okay, sir.
So yeah, any answer
Thank you.
to this?
Thank you.
Any answer to this problem? Okay, so let me do it then by myself. So this is a simple problem only. So it says 1 mega, which is nothing but if you can make 1 mega into kilo, so it will be 2 raised power 10. That is 1024 cross kilo, right? I mean 1 MB. I mean you already might have seen it is 1024 KB. That is what I have just said. And here it says 1 mega memory from 64K. So I can do what I can do is 1 mega cross 4 using 64K cross 4. So this is 2 raised power 10K cross 4, and this is 64, which is 2 raised power 6 cross k cross 4. So basically these many memory units are required, which is 16, right? Huh. So basically 16 64k cross 4 memory cell will make 1 mega cross 4. So your answer will be 16. Is it clear? Okay, let's move ahead then quickly. So the next problem says SRAM stores the binary information in. Oh, please let me know the answer quickly. Maybe take 1 minute and type your answers in the chat box. Okay, so I have answer which is B. So the let's see, go through all the options. So it says a form of electrical charges on a capacitor. So this is basically 1T1C DRAM. The question is asking about SRAM. So yeah, option B is correct because in SRAM we have these internal latches where Q and Q bar are the storage units. Inductor is not there and lookup tables are not there. So yeah, option B is the correct answer. Okay, let's go quickly. So which of the following statement is false? Please let me know your answers again in the chat box.
What is lookup table, sir?
Yeah, so lookup table is actually a method to store. So actually it is out of scope of this particular course, so that might not help. But yeah, so these are types of model in which what we do is we see the input and output and we make a table which is basically the relation between the input and output, and that is what we call as a mathematical model. So I mean that even does not have a memory. That is a model that can we can only use just to store. We cannot store anything using lookup table. We can only what to say, function some of the transistors using lookup table. We can make a mathematical relation between them. I mean, yeah, it is out of the scope, so don't worry about it if you are not able to understand what I just said.
Okay, sir.
Okay, so any answer to this? I got one, which is D. This is a simple question. I mean, I've already explained, I think, all of these. So, okay. So let's go one by one then towards all the options again, if you are not able to answer it in a first go. So it says SRAM memories has a shorter read write than compared to DRAM, right? So this is correct because of the quick working of it. So as I said, SRAM is used in cache, which is the fastest memory. The first problem itself I said, and it also contains more transistor to make it quick. DRAM is slower because it has a capacitor and it is very slow to charge or discharge this capacitor. So DRAM is actually slow. So this is actually true. So this cannot be the answer. DRAM memories has a longer read write. Yeah. So this is again the same statement opposite. Now the next statement is SRAM memories occupies minimal area compared to DRAM. So the DRAM only has one transistor, whereas SRAM has six transistors. So it is highly expensive also, and we can say high area occupation. So okay, so the last statement should be correct, and the correct answer would be option C. So the only false statement in this is option C.
Sir,
Yeah,
sir, static RAM uses six transistors, no, sir?
yeah,
And high area how- occupies SRAM memories occupies minimal area compared.
yeah. So this is false statement. The question says which is false.
Okay, sir. Yes.
Okay, so we have a next problem which is programmable array logic contains. Okay, so let me write by myself only. So we have two circuits. One is called as PLA, one is called as PAL. So the PLA, it has a programmable and programmable OR. Then we have PAL, in which what we have is we have programmable and fixed OR. There is one more which is called as PROM. I don't know if it is in the syllabus or not. In this, what do we have is we have a fixed and programmable OR. So the question is asking about PAL, and it has a programmable and a fixed OR, which is option C is the correct answer. So we'll do some problems regarding related to this in later in this lecture only. So let's move ahead. So which of the following technology is not programmable? Okay, so again this is a theoretical question only. So EEPROM is actually electrically erasable programmable ROM. EPROM is again electrical programmable ROM. So this is programmable, this is programmable. Fuse. Okay, so fuse is like a buffer circuit. I mean, you might have seen in your problems when you were doing the PAL and PLA circuits. So fuse is nothing but where you make those X connections. So it is like a combinational part. This is not programmable. This is like fixed. And SRAM we have just seen, we can do whatever we want to. So it is also a memory. So option A is the correct answer. I think I can also call it as reprogrammable because that would be a correct term to say. Okay, is it fine? Let's move ahead. Which of the following memories is volatile in nature? Anyone quickly?
Yes, Ram, sir.
Yeah. So we just studied that SRAM or the RAM is in general volatile in nature. ROM is permanent. So yeah, this is again theoretical. So let's move ahead. Okay, so this is one again a simple problem we have. I think we have just done that 2p raised per m problem, if you remember. So it says what is the ROM size when it has 16-bit address lines as input and 8-bit data lines as output. Okay, so you just need to replace M and L and you'll be able to get the answer. Please let me know in the chat box quickly. So if you remember, we had, sorry, this was N, I think. So we had this P as address input lines, and my N was input lines, or the, sorry, it was data lines, I think. So okay. Oh, it's already given. I thought we need to calculate something. So it is 2 raised by 16 cross 8, which is option, yeah, option A is the correct answer. Okay. Okay. Yeah. So we have a similar problem again. It says a memory unit 1024 cross 64 is specified by the number of word times the number of bit words. Okay, so number of word is basically this, and number of bits per word is this. It says how many address lines are needed. Again, this is the same question. You can try it out and let me know in the chat box quickly. Oh, I've already got one answer, I think. C. Okay. I'll wait for one more minute quickly and then I'll also solve it. So please everyone type your answers in the chat box. Okay, I've got one more, so let's do it. So it is 1024 cross 64, which let's say we equate it to 2 raised by k cross n or p, sorry. So as a question suggests, 2 raised by p is number of words, n is number of bits per word, and we have already seen that k is, oh sorry, p is nothing but number of address lines. So basically 2 raised power p in the question is 1024. So p will be nothing but 10. So yeah, option C is the correct answer. Okay, let's move ahead. Okay, yeah, so we also have this particular Hamming code topic, I think, in this week only. So it says which of the following statement is true? Anyone wants to? Okay, so let me tell you a very basic of this. So Hamming code is nothing but it is like a technique which can detect and correct errors in some of the your some of the movement of the bits from one place to another. So Hamming code, it has its own limitation. It can detect multiple bits, but it can only correct single bit error the way it works. So Hamming code, what it can do is it can correct one bit and it can detect 2-bit errors. So I mean, based upon these, only option A is the correct answer because 3, 4, and 2 are not possible. So let's do some of the problem related to Hamming code. So it says what is the size of Hamming code for a 10-bit data byte? So is anyone already aware of this? I mean, I don't know if it is already covered in the lecture or not. Can anyone confirm? Okay, so it will not. So it is like a 10-bit data byte. So Hamming code is nothing but total size of the Hamming code is n plus k, where n is the data bit or the bit of data word, then k is number of code bits. So the total size of the Hamming code is n plus k, and Hamming code, the condition for the Hamming code is 2 raised per k minus 1 should always be greater than equals to n plus k. So you just need to apply these conditions. So we already know the value of n is 10. So we'll do 2 raised per k minus 1 should be greater than equals to 10 plus k. Okay, so this will give me 2 raised per k greater than 9 plus k. Okay, so we need to find k first, and then the total size of the Hamming code will be n plus k. So can anyone tell me what will be the k quickly? So what we can do is we can use different k values and see. So we can start from 1, then 2, then 3, then 4, then 5. So if we keep 1, so 2 greater than equals to 10, this is incorrect. So if I keep 2, so this will be 4 greater than equals to 13, this is incorrect. 3, we have 8 greater than equals to 12, this is also incorrect. 4, we have 16 greater than equals to 13. Yeah, so this is correct. So k will be 4, right? So we have 4 sk, so n plus k will be 10 plus 4, which is 14. Size of Hamming code will be 14, which is option B. Okay, not 9, it's 11. What is 9 and 11 here? Uh, oh yeah, yeah, I got, sorry, yeah. Okay, yeah, so again I don't know, so it will be 2, then this will be 13. Oh yeah, so this will always be 13. No, so k is 2, so this will be 13. K is 1, so this will be 12. K is 3, so this will be 14. K is 4, so this will, yeah, so still, I mean, yeah, the answer is still correct because k is still coming out to be 4. Sorry for that. So the answer would be 14 bits.
Sir,
Yes.
is this Hamming code now using in real world, sir? I mean, now there are digital circuits in the world now,
Yeah,
sir.
yeah, yeah, yeah.
Are they using the Hamming code now, sir?
Yeah, yeah. So to check the correct error or just to correct single bit error it can be used. So there are actually a lot of codes that are there in the literature. So Hemi code is let's say the most basic version of them. And yeah, we'll study it. I mean, how actually it works. And I mean, I would say that currently in the circuits, due to their complex nature, there are various more advanced codes that are there. So yeah, but Hemi code was a basic fundamental code that was used or that was invented initially to correct and check the error in the parity bits. So yeah, let's do a problem maybe that will help. So let's do this problem first because it is easy. So it says find the 12-bit Hamming code for the given 8-bit data. So I'm assuming you all are not aware about Hamming code. I don't know. So let me do it by myself then. So Hamming code is, so since this is a 12-bit Hamming code, so we have 12 bits. 1, 2, 3, 4, 5, 6. So just to give you explanation, there are 8-bit data. So the remaining 4 bits are also called as parity bits. And they are stored at a location of 2 raised power k. So basically k is from 0 to n. So the parity bits will be 1, 2, 4, 8 and so on. So for this question there are 4 parity bits. So one is P1, one is P2, this is P4 and this is P8. And the remaining thing that was left is the actual given data. So this is 1, 1, 0, 0, 0, 0, 1, 1. Is this part clear? We need to find the 12 bits, so we need to find the parity bits for that. Is it clear till here? Okay, to calculate the parity bits, we have the formula which is, so for P1 it is XOR of 3, 5, 7, 9, 11. For P2 it is XOR of 3, 6, 7, 10, 11. For P4 it's 5, 6, 7, 12. And for P8 it's 9, 10, 11, 12. You just need to do the XOR of these things and you will be able to calculate P1, P2, P3, P4, and then you can find the overall data word, or sorry, the Hamming code. Is it clear the steps that are involved? Please let me know if it is clear. Okay, so what I'm saying is we have a 12-bit Hamming code. So I've used 12 numbers, different numbers. Then from the 12 bits in general, 8 bits are the data word and the 4 bits that are remaining are the parity bits. And parity bits are always present at 2 raised power k, that is 2th location. So it can be 0, it can be 1, it can be, sorry, not to 1. Sorry, it can be 1 because k is 0, it will be 1, 2, 4, 8, 16 and so on. So what I've done is at 1, 2, 4, 16, not 16 but 8, I placed the parity bits and I have written the given bit words sequentially after that. So now to calculate the Hamming code, we need to calculate P1, P2, P4, P8. And to calculate P1, P2, P4, P8, we have the XOR of these bits. So we need to do the location of 3, 5, 7, and 11. For this, we need to do 3, 6, 7, 10, 11, and so on. Is the way of doing it clear? Those who asked, I don't know who asked. Yeah, so we'll do the XOR of, for example, okay. Are you asking how we'll do XOR or why I'm using these 3, 5, 7, 9, 11? What exactly is your question? Can you please clarify? Okay, so how that come? Okay, so that is actually a good question. So if you go, for example, so you have 12 bits. Okay, so what was that? P. 4 P3, yeah. So if you have 12 bits, for example, so it's 0 0 0 0 0 0 0 1 1 1. Then we have 4 5 6 7 8 9 10 correctly. Then we have 11. Okay. So for P1, we take the bits where the LSB of these bits are actually 1. So for example, what I'm trying to say is, so it is 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, right? So this is actually 1. So 1 I have not written because it is actually occupied by the parity bit itself. So we'll only use this one when we are checking any code. But the parity bits itself contain 1, so we are not using 1. So then we have 3, then we have 5, then we have, what is this, 7, this is 9, this is 11. So this is how the 3, 5, 7, and 11 come. Similarly for 2, we have where the second bit is 1. So I can also do that just to explain. So it's 1 here, 1 here. Yeah. So now you see the first one is 2. So 2 I have not written because it is already occupied by the parity bits itself. Then we have, what is this? This is 3. Oh, no. Oh, okay. So this is 3. Then we have 6. Then we have 7. Then we have 10 and 11. So this is how P2 come. Similarly for P3 we'll have, or P4 we have when the third bit is 1, and similarly for P4 we have, or P8 we have when the final bit is 1. Is it clear? Okay, so let's do it quickly now. So we'll just write the corresponding bit. So 3 is 1, 6 is 1, 7 it's 0, sorry, 9 is 0, and then 11 is 1. Then 3 is 1, 6 is 0, 7 is 0, 10, 11 is 0, 1. Then we have 5, 6, 7, 12. We have 1, 0, 0, 1, last 0, 0, 1, 1. So the output of these XOR will be, we have even numbers of 1, XOR will give the, we have done it as a topic named as parity generator, if you remember. Yeah, so it's give 1. So this is like a output will be 1. Then if you have even ones, it will be 0, this will be 0, this will be 0. So the parity bits will be 1 0 0 0. So if I can replace that, maybe I can use some different thing. So this is actually 1 0 0 0. So the actual 12-bit number will be, if I write here, so it will be 1 0 1 0 1 0 0 0 0 0 1 1. Is there any option like that? 1 0 1 0 1 0 0. Yeah, option B is the correct answer. Is it clear to everyone? Please let me know. Okay, yeah. So yeah, so one more advanced version of this problem is this. It seems to be very simple, but yeah, let's do it. So it says a 12-bit Hamming code, again read from a memory location. This Hamming code contains 8-bit data and 4-bit code word. What is the original 8-bit stored in the memory if the 12-bit Hamming code is this? So it says it's 0 0 1 1 1. Sorry, let me write it in a 0 0 1 1 1 0 1 1 1 1 1 0. So I can write again 1 2 3 4 5 6 9 10 11 12. So I can write this as P1, P2, P4, P8, and the remaining thing will be the data word, right? It's 1 1 0 1 1 1. Is it clear till here, everyone? So yeah, if you see like that, so the correct answer should be option B, right? Because we are getting the bits as 1101 and 1110. But actually this is incorrect. I'll tell you how. So whenever you see a Hamming code, you always have to check it if there is any error in those parity bits or not. So as we have just calculated the parity bits by doing the XOR, we always need to calculate if there is a given Hamming code, we always need to calculate the check bits. So the checked bits are nothing but the parity bits. So let me try to explain that. Yeah. So again, the C1 will be exactly same as the parity bits. It's the only difference is it will contain that bit itself. So we need to check. So it will be 1 and the parity 1 was 3 5 7 9 11. Then we have C2 which is XOR of 2. Then we have 3 6 7 10 11. Then we have C4 which is XOR of 4, and then 5 6 7 12. That was there before also. We have C8 which is XOR of 8, and then 9 10 11 12. So your Hamming code is correct. Sorry, if C4's whatever this is, maybe I can write C8 C4 C2 C1. If this is equals to 0 0 0 0, that means there is no error in the Hamming code. If let's say there is a finite number, whatever this is, then this position contains error. So it can only detect a error of single bit. Is this clear to everyone? The way I've just told what we need to do?
Sir, for suppose 0, 1, 0, 0, that means C4 has error, sir.
No, no, no. So, okay. For example, 0 1 0 0. So this is actually fourth. So fourth position has error. I mean this position.
Okay, sir.
Yeah. C and previous PR. No. So the only difference between C and PR, the parity bits are added here. So this is actually the previous P, and we have also added to check because parity bits was getting consumed itself. So the check bits we need to check the parity also. Otherwise, yeah, they are same. So if the question is clear, please let me know the answers. Maybe even take 2 minutes, and then yeah, we can see. Okay, let me also do it side by side. This might take some time. So yeah, 1 is 0, 3 is 1. Please quickly let me know what is C8, C4, C2, C1. If you have already calculated. Let me try to do it quickly myself. 7 9 11 is 1, 2 is 0, 1, then 0, then 1 1 1. That should we have 1 1 0 1 0. 8 9 10 11 are all 1. So 1 1 1 1 will be 0. Okay, so C1 will be 1 2 3 4. So there is 5, so it will be, sorry, odd. 1 2 3 4. So this will be 0. E4 will be 1 1. So even, okay, so this will be again 1. E1 is 0. Okay, so C8 is 0 1 0 1. I hope I've done it correctly. Are you also getting the same? Anyone who has calculated it? So this means error in fifth position. So basically this is not 1, this is actually 0. So the actual Hamming code is or the data one, I can even only write the 8-bit data is 1001 and then 1110. Is there any option like that? Huh. Option A is the actual correct answer. Please let me know if it is clear to everyone. This is important topic. I think this is covered in this week's lecture only. I'm not sure about that. Please go through those lecture if it is already not covered. Are you also getting the same answer, everyone? Okay, yeah. So now we have some more questions on PAL and PLA. So these are actually easier question. Just we need to do some more calculations. I hope you can see the connections clearly. So it says we have a given circuit, identify the output A and B. So this is and, I mean, you can clearly see. So we have and here, and then we have or here. So all are programmable. There is nothing fixed. So both programmable means this is a PLA circuit. So we need to find actually just A and B. Maybe you can take 2 minutes and let me know the answer. This is very straightforward actually. Do you want to try it? Okay. So maybe I can do this. So this is connected, which is X. This is Y. So this output will be XY. Then this is X. This is Z bar. This will be XZ bar. This is X. This is Y bar. So this will be XY bar. This is Y. This is Z. So this will be YZ. Now, so A will be OR of this and this. So A is XY plus XZ bar. And B will be OR of these three, which is XZ bar plus XY bar plus YZ. So is there an option like that? Um, oh, XY plus XZ bar, XZ bar plus XY bar. Yeah, so option B is the correct answer. I hope I've done the calculations correctly. Is it clear to everyone? Okay. Yeah. So let's move ahead. Maybe, yeah. This is a more complex problem, I would say. But again, this is simple only. So it says what are the outputs of the following circuit. So it is the same PLA, just it has two more connections of XOR gates. So XOR, you might be knowing that there are, if we make 0 XOR X XOR 0, so this will be X into 1 plus X. So this will give you the actual output and this will give you the complement of the output. So here one of the XOR gate is connected to 1 and here one of the XOR gate is connected to 0. Do you want to try it by yourself? Please let me know, otherwise I'll solve it. Okay, so let me solve it then. So okay, so this is B bar, this is A. So the output of this will be A B bar. Maybe I'll write here. This is C and this is A. So this will be AC. This is B, this is C, so this will be BC. This is so we have C bar, B, A bar. So A bar, B, C bar. Okay, so maybe I'm calling this as X and I'm calling this as Y. So X will be AC plus BC. Y will be A B bar plus AC plus A bar B C bar. Is it clear to everyone? So F1 will be basically this is Y. So Y XOR 1, which will be actually give you a Y bar, and F2 will be 0 X XOR 0, which will actually give you X. So F2 I can clearly say is X is AC plus BC. So two options have this, and the complement of this will be F1. So complement of A B bar plus AC. Yeah, so option A is the correct answer. Any doubts here? What is mail ID, sir? What do you mean by that? Oh, you want my mail ID? Okay. So I'll write in next page so you can try out this problem. And my mail ID is this. Yeah. This is not actually visible quite a lot. So let me make the connections. This is again a same problem. It's just that we need to do the canonical form, or we need to find the minterms. Is it the exact same problem or is it something else? The connections are different here, I think. Okay, so if you have a doubt in last week, so maybe you can mail me and I'll let you know what could be the correct answer. So let me try this problem then. So this will be C bar A bar. So I'll also like you guys to try it. So of both of them. So let A bar C bar. This will be C B A B C. This will be B bar C bar. This will be C and AC. So okay, X Y. So I'm again calling this as X and Y maybe. So Y will be ABC plus AC. AC plus ABC, and Z will be A bar C bar plus ABC plus B bar C bar. So now F1 is Y XOR 1, which is actually Y bar. So this means AC plus ABC whole bar. F2 is X XOR, oh sorry, did I write correctly? X XOR 0, yeah. So this will be X, and that is actually this thing A bar C bar plus ABC plus B bar C bar. Oh, actually I can see that we can take common of AC here, AC bar. So this will be, I think, AC bar, right? Hmm. So yeah, F1 will be AC bar, and then F2 will be this long term. So if I try to write F1 in terms of min term, we can make a quick K map, maybe that will be easier. Oh yeah, let's say A bar A, B bar C bar, B bar C, B C, and B C bar. So A bar is already there, C bar is here and here. So okay, I need to write that 0, 1, 2, 3, 4, 5, 6, 7. So F1 is actually min term 0, 1, 2, 3, 4, 6. Is there any option like that? Oh, so there is a single option like that. So option A is the correct answer. I'm assuming F2 will come out to be 0, 2, 4, 7. I'm not doing that again. But is it clear to everyone? Okay, so try out maybe again. So this is again a simpler problem. So let me know the answers quickly in the chat box. I'll give you 2 minutes. Okay, so let me quickly try it out. So this is C bar and this is B bar C bar. I can use different color. This is B and B bar. So this is 0 actually. Sure. A C bar B A bar B C bar. This is ABC. Okay. So I'm just writing F1, F2, F3. So this is actually very easy. So F1 is 0 is 1. So B bar C bar and ABC. So ABC plus B bar C bar. F2 is 0 is this. So ABC is F2. F3 is this thing, whatever this is. A bar B C bar plus B bar C bar. Is there any option like that? So F1 is A B C plus B bar C bar. Oh, these two are both. F2 is ABC, F2 is AB. Oh yeah. So I think option B should be the correct answer. Let's check F3. A bar B C bar. Yeah. So option B is the correct answer. Is it clear to everyone? Okay, great. So yeah, so these are all the major problems that I had for this lecture. Yeah, so this was which option A. So this lecture particularly contained that PAL and PLA topics, and one more important topic was Hamming code. So I hope I was able to give you some of the basic idea to solve the Hamming code problems. I did see that there are some of the problems in your week 9 assignment problems in your current assignment. Then we also like studied some of the basic about this SRAM DRAM and see a very like rough idea of how actually read write and hold operation happens in SRAM and DRAM. So yeah, if you have any query, please let me know. Maybe in the next week we might continue with some of the memory topic, and or we might move ahead to the microprocessor topic. I'll see the assignment for week 10 and see accordingly what exactly do we need to study about that. So yeah, if you don't have any doubts, I think we can wrap up the session quickly. Uh, so is there any doubt, anyone? So if not, I think yeah, we can wrap up the session and we'll meet next week, same time. Thank you everyone for joining.